So we are happy to welcome Jazzie. So the floor is yours.
Okay. Good afternoon, everyone. So I'm Jazzie Jao. So I'm together with my author in writing this paper, but he's not here, so I'm the one in charge of this. So I'm from the Department of Software Technology, College of Computer Studies at the Southern University, Philippines. Before we start, this is going to be the outline of my paper. So introduction, objectives, the methods, and the results in summary. Just to give you an overview about the municipal solid waste, so it has been one of the challenging sectors to manage because first, its complex nature, the quick growth of waste amount brought about by the development and high management costs of the developing and developed countries. So this problem is not just observed in developed countries, but also in developing countries. Good waste collection service is essential because we have different stages of solid waste management, right? And the waste collection service is essential to upgrade further the next levels of a municipal solid waste system like waste segregation, recycling, and recovery, which are also important. One of the ways to enhance performance on waste collection is to plan effective routing of trucks. Now, the routing problem has a lot of we can see a lot of research on route optimization, which are framed either a node routing or an arc routing problem. We also have the general routing problem, which considers both of the conditions, but I'm just discussing this one. So typically, waste collection service can be modeled as a node routing problem, wherein the people to be serviced are located or modeled as a point. On the other hand, the arc routing problem is waste is to be collected along street segments. So these are treated differently when we model the problem. Now, this study specifically uses the single objective ARP or the arc routing formulation, and the objective function to be minimized is the distance taken, and we also considered another objective function, which is the CMEN, which I will discuss or give an overview later. Other measures like fuel consumption and greenhouse gas are also calculated using this model, where the load and speed of the collection vehicle are included in the predictor variables. VRP is one of the intractable problems in regulatory optimization that can only be solved with exact method of solution when the problem size is small. Now, when the problem size gets bigger, this is where the approximation methods comes in, and one of that methods is the EM-RIGHT algorithm, which is actually under meta-heuristics. So EM-RIGHT algorithm is a physics-based algorithm used to solve the waste collection routing problem, formulated as a single optimization one. Now this is the road network of the area, so it's situated in the Philippines. This is the real data. And we transform this one in this graph. So this one is I think this one is the road network graph. So the DCAE, so the numeric variables here are the intersections, while the numerical alphabets, while the numerical values here are the segments. Now we transform this one into the directed multigraph representation because we want to consider the two-way explicitly if the street is two-way or not. Because we can use this information to model the time dependency when the traffic conditions are considered. But we can also have other formulations here. Some problems model this one as an undirected graph or a directed graph only. Now the problem design, we have here the baseline scenario of the ARP. So this is the objective function where L is the road length of the ith street and O is the number of elements in this path constructed. So this is the objective function. And we also have another objective function, which is this one. So we treated this one separately, that's why it's single objective. We did not treat it as simultaneous. So the other objective function is the CMEM model. So this is the reference of that, wherein we have the following variables that considers the length of the street, the speed of the vehicle, and the load of the vehicle. The reason why we want this to be in the picture is because we can see later on that minimizing the distance does not really lead to minimizing the cost as well in terms of fuel because we have this load. So these are the parameters of this model, which you can check later on. This can be changed, obviously. Depends on what kind of truck you have. In general, the waste collection will always contain street segments that are traversed more than once. So we have this equation that is guarantees that if this street segment is appeared first, then it's considered as a factor with one, and if it appeared more than one, then you will not consider that already. So this is the EM-like algorithm. So we have two equations, two main equations here. So EM-like is electromagnetism-like, so it's based on physics. Physics, we have charges and we have the force. So here, the force here is, okay, so before I discuss the force, this is the force and this is the charge. Before I discuss that, the EM-like is a population-based algorithm. So it means that we have to generate several solutions first before we approximate what is the best among them. Now, the aim of this generating a set of report solution is we want to permute the set of streets to service in order to get the optimal permutation. And this optimal permutation is now the series of streets to service. Now, this permutation is embedded in the search agent of the EM-like, which is this particle. So this particle, in a way, is containing the permutation of that. So after initializing the populations, the next step is to calculate their charges according to this equation. So unlike the traditional charges in physics, these assumes that it's always positive. Because in physics, we can have negative charges, right? The variable n here is the number of dimensions. In this context, the number of streets of the path. And the function, objective functions f of x sub I and f of x sub j, this one, are the objective function values of two particles. So it's assumed that these I and j are distinct when we calculate this one. That's just what it means. Next is to implement how new solutions are produced from the previous one. How do we evolve from these initial solutions that we have? So what you can see in here is the mechanism of how new solutions are generated. So it uses the attraction repulsion of charged particles in physics to utilize the positions of particles. So the positions of particles are given as x sub j and x sub I. So x sub j and x sub I, so in general this is considered as a vector that's composed of several components. So the fitness value is embedded to the magnitude of their charges, it's this one, and calculated in the previous section, or this. So after that, okay, so before that, notice that the equation in the red box is expressed in vector form. It's because we are assuming that the particles are placed in an n-dimensional space. As such, it's considered that each particle's position is composed of n components here. On the other hand, so if you recall the physics concept here, the two conditional statements here, the first one and the second one, so this one is needed because we have to specify between x sub j and x sub I, which of these has better objective function value. Now, we are dealing with a minimization problem. So therefore, the definition of a better solution here is the one with the lower cost. So the first statement means this one. It means that if particle j has better, so if particle j, this one, has better function value, then it attracts particle I, and the direction of the displacement is towards particle j. Because that's the mechanism. If some particle is better than that, then you attract all of the particles there. Okay, so that's also similar here. If particle I has better solution over particle j, then particle I attracts the particle j. And after getting the resultant force of this one, the amount of movement of this one will be obtained such that we can get another set of particles. So we repeat this process until we define a termination criteria, like maybe if we reach a specific threshold, the number of iterations or computational research that we have. So for the results in summary, so these are the parameter settings. So since this is a approximation algorithm, we try to modify what happens if there is a local search. So the local search is, it can be seen as if some particles, if there is cluster of particles in one location, then we encourage these particles to search near it. Some of the settings are not embedded with local search so that we can compare. Particle movement boundary, so this is seen from what is the boundary of the particle movement of each charges, how it also affects that. We have this between 0 and 1, and we also have this random values. So these are some of the results here. So as you can see here, the alpha CBLO obtained better distance value compared to the one with a different parameter. So in general, minimizing the distance does not lead to minimization of the corresponding cost due to fuel consumption because we have the loads there, we are collecting waste. And this is because we can also interpret it in a way that the lack of capacity considerations forces the truck to be overfilled, thus increased need to consume fuel. So these are some of the results of the simulations. So in general, there is a decreasing value for each of the starting from the initial population. So we run this one for 2,000 iterations. This is quite few. We could have run this for maybe 100,000 or 50,000, which is better than just 2,000. So I think there is a convergence problem, specifically this one, because it gets trapped to some place instead of exploring the area. Even though you're continuously running for every iteration, it does not go out of this exploration location. That's why it's just a flat line like here. So it encourages the exploration phase. So that's one of the disadvantage of EM-like algorithm when applied to discrete optimization problem, because this one is a discrete optimization problem. The EM-like is initially applied to continuous optimization problems. So I think this is the disadvantage of using such transformation. So based from the results, we need to consider the capacity. That's why in other literature, they have this capacitated R crowding problem because they also already considered that one. And maybe we can also try to get the behavior of permutations across iterations. Like what happens so that even though you're changing the permutation, why is it not the case that the objective function value is not changing? That's also a good research. And to improve the speed convergence, it's suggested to hybridize algorithm. So maybe we can apply single solution based algorithms to do that, like simulated annealing aside from the population base. And in conclusion, it behaves or it displays significant minimization and 39% of solution improvement compared to the traditional one without the local switch. So that is the end of my presentation. Thank you very much.
Thanks a lot, Jazzie. Do we have any questions?
I have no questions. I think that's